Oh, I forgot. My office hours today are from 2 to 4. So function notation. So a lot of what we're going to talk about today, as the name implies, really has to do with notation. Mathematically, and as far as like calculations go, like none of this is anything that you haven't done before. What we're talking about today is mainly just the way that we express functions algebraically, and the way we use that notation to, like I said, do things that we've done before, like evaluate expressions and things like that. At the beginning here, it might seem a little bit like we're overcomplicating something really simple, because we kind of are. But as the functions that you work with get to be more and more complex, and as you work with more and more functions as part of a single problem, it starts to become really clear why having this specific notation is really useful. So let's talk about the notation, and then I'll try to point out some reasons why we use it, so it doesn't just seem like we're writing all this random stuff just for the heck of it. So we can think of y equals x plus 5 is a function. So it pairs each input with an output based on the rule the output is 5 more than the input. So y equals x plus 5 is probably an equation that we've all kind of seen before, something like that. But what this is really doing is describing a relation, like we talked about yesterday, in which our inputs are just numbers, our outputs are other numbers, and the correspondence between them is that to pair an output with an input, the output has to be 5 more than the input. So just like we talked about yesterday, this is a relation. It happens to be a function because if you take any number, there's only one other number that's 5 more than it. It is impossible to add 5 to a specific number and get 2 different numbers, right? And so for every input, so every number that I input into this function or into this relation, I'm going to get exactly 1 output corresponding to it. And so that makes this a function. One thing to keep in mind about functions is their relationships in terms of like operations. So they describe a set of operations. So in this situation, this function is saying add 5 to the input to get the output. Functions don't really have anything to do with x's and y's and a's and b's and c's and d's. We use symbols like variables to represent them because it's a lot easier to write what's on the left side than to write what's on the right side every single time. But in reality, the function itself is about the operation it's performing, not about the variables that we happen to use to perform that operation or to represent that operation in writing. So we always want to think of operations in terms of, functions in terms of the operations they perform. If we think of a function as just y equals x plus 5, that's sort of a narrow way of viewing it, and it's hard for us to then extend that idea to ideas that we'll talk about later this week, like domains and ranges and things like that. So in function notation, we don't use y's in this equation. We write this same relationship is written f of x equals x plus 5. So there's a lot to this notation. The first thing to think about is this letter right here. This is the name of the function. It does not behave like a variable. So f itself does not represent a number. So when we think about variables in terms of like x and y and z and a and b, they're just letters that we use to represent numerical values, right? In this case, f is just a name. So the function f is the function that adds 5 to its input. But f itself doesn't have a numerical value. It just tells us which function we're talking about or which relation we're talking about. This right here tells us the input that we're using for the function. So x is really just a dummy input. It's like a placeholder so that we have something to write there as a general input of our function. So this is the input of the function. This entire right side is our rule. So it's the correspondence we talked about yesterday that tells us how to get an output from a specific input. So this is the rule. For obtaining we have a budget request in for new technology. I don't know if it'll get here before you guys get to sit and stop sitting and watching me struggle with old technology, but it would be nice if it did. Okay. That should do it. For obtaining an output from your input. And then the last piece, which is really two of these pieces combined, is f of x is how we read that. That whole thing together is like a variable. That whole thing, f of x, represents the output of the function. So this is the output of the function f which, well, no, corresponding to an input of x. So that whole thing, f of x, is how it's written, or how it's read, f of x. That whole thing is like your y. So one of the tricky parts of this whole thing is that it looks a lot like f times x, but it's not the product of two different things. F of x is in and of itself a variable to represent a value. Within that symbol, it tells us what the name of the function is and what input we use to get that output. So f of x is the output of the function using the input of x. So that means that f of, say, 3 is the output of the function f, which corresponds to an input of 3. So f of 3 in this case would be 8, right? Because if you take 3, your input, and you add 5 to it, I did say 5, right? Yes. You get 8. So the input here is 3. The function we're using is f, and the output corresponding to it is 8. One way you can think of this is like an ordered pair. So this is like the ordered pair 3, 8. The only reason we use function notation is because when we get to a situation where we have more than one function, if we have a ton of ordered pairs, like the one on the right, floating around, with no way of knowing which one is on the graph of which function, that gets really, really confusing. Whereas if we write it as f of 3 equals 8 and g of 9 equals 7 or something like that, then we know which one of those ordered pairs is on the graph of f and which one of those ordered pairs is on the graph of g. So this is essentially just another way of writing an ordered pair, but with the added bonus that we're expressing which relationship we use to get that pair right there within that statement. Does that make sense? A little? Okay, let's evaluate some functions. Another way a lot of people think of it is like functions are like machines, right? You start with an input. And you put it in the machine. My high school teacher had a much better way of drawing a machine than I do, but I have no artistic ability whatsoever, so we're just going to make it like a box. And we name that machine F, and then it spits out your output. So if I started with the input X and I put it into F, it's going to spit out f of x. If I start with the input like 9 and I put it into f, it's going to spit out f of 9. And so on and so forth. If I start with the input star and I put it into my function, it's going to spit out f of star. So that has no mathematical meaning whatsoever, f of star, but I do know that it's the output that I got from the function f when I put in the input star, right? Like symbolically, none of this means much mathematically without the rule that goes with it, but we can see how f of whatever just represents the output associated with whatever the input is. So we can think of like whatever my input is, I put it into my function, and my output is f of that input. And this is the reason we don't want to get hung up on the x's, right? Because that input could be anything. It can be any number, it can be any variable, it can be a whole expression, but f tells us how to evaluate it. So let's evaluate, let's say, let f be defined by the rule multiply by 5 then add 3. So like I said, the actual rule itself is just telling us a set of operations. In this statement, it tells us the name of our function is f. So if I want to write this in function notation, I'm going to start with the name of my function, and then I have to decide on an input. And really we pick something, and we could pick anything we want to represent our general input, but let's be real, everybody uses x, so we'll just use x. So f of x. So x is my input, now I have to apply that rule to it. So starting with x, I'm going to multiply by 5. That gets me 5x. You can write it as x times 5, but as far as working with these algebraically, we're more used to seeing x times 5 as 5x. So I usually just do that switch and then add 3. So f takes an input of x, multiplies it by 5, adds 3, and gets 5x plus 3 as the output. So we can then evaluate this function. How about negative 10? So if I want to evaluate f of negative 10, this is exactly the same as what we did last week on our very first day when we said something like, evaluate the expression 5x plus 3 for x equals negative 10, right? I'm giving you an expression, in this case 5x plus 3. I'm giving you the input negative 10. The only thing that function notation adds for us is this name for the function, or the name for the expression that we get by applying the function. And again, that's going to come in really helpful when we have multiple functions going on. The best example I can give you that we'll see later in the semester is like when you're doing business applications. So when you deal with like profit, cost, revenue, price, all of those are based on the quantity that's being produced. And you get 4 functions. You get a price function, a cost function, a revenue function, and a profit function. And if you don't name them all different things, then all of a sudden, like, things get crazy, right? You've got one formula for one thing, one formula for the other, and you can get lost really, really easily. And so we can use this function notation to name profit, capital P, and name cost, capital C, and then we can keep everything straight as far as what we're trying to find in any given problem, even when we're working with all of these different rules. So to evaluate f of 10, all I'm going to do is replace my general input of x with the input negative 10. So we have f of 10 or f of negative 10 rather, says to multiply negative 10 by 5 and add 3. These always have to match. So the input used in the notation on the left has to match the input that you actually used in the calculation on the right. So on the right, we're doing a calculation with some input. On the left, our notation has to reflect that. So you would never, in this case, write something like f of x equals 5 times negative 10 plus 3. If you replace the x on the right side in your calculation, you also replace the x on the left side in that notation. And you guys are probably going to get really annoyed with me all semester about grading you based on your notation, but in reality, again, the notation of this is really the only thing that's new, right? Like, you guys know how to multiply 5 times negative 10 and then add 3 to it. So what I really want to know is that you're understanding the new language that we're using as far as expressing this stuff using function notation. So keeping that in mind, the left side of this equation is just as important as the right side. I know the right side is the one that spits out a number for you, and we all really want to write a number on a line, but the left side is just as important. It's hard to see why it's so important in this setting because there's like literally 2 calculations to do, and like at the end we're like f of negative 10 equals, oh crap, negative 47. And that's a 2-liner, right? But again, as you progress in mathematics and get yourself to calc and calc 2 or however many calculuses you plan on taking, these problems get a lot longer. And if you have a page and a half in between that first line and that last line, we don't really want to write this and then come like 2 pages later and be like, negative 47. Because by then we've forgotten what the heck we started with. Like, whereas if a page and a half later we write f of negative 10 equals negative 47, that one concise statement tells us what function we used, what input we used and what the resulting output was, right? So it gives us every single piece of information that we need about what problem we solved right there in our final answer. So we don't have to ever go searching back through all the work that we did to be like, oh yeah, I was using F and I started with an X value of -10 to get that -47. So this whole thing is like our answer, and in it, it has all the information about the original problem that we were solving. I am happy for you to write the left side just once, as long as you line everything up nice and vertically. So if you line up your equal signs vertically as you do your calculations, you don't necessarily have to write that F of -10 in every single step. If you are a person who, for goodness sakes, I need to get a backup pencil. If you're a person that doesn't necessarily like write your work super organized, like if your first step is like over here and then your second step is like way over there, then you should write the left and the right side in every single step. Does that make sense? So like if you can line it up nice and neat so that I clearly know that the left side is equal to the right side in every step, that's totally cool. If it's kind of all over the place, one step here, one step here, one step here, then write the left and side and right side every single time. If you're ever not sure if your notation is correct, you can just snap a picture and send it to me, and I'm happy to tell you, like, no, you need this on the left side or whatever. Okay, so I'm going to have you guys do this one. Let's use the same rule. We'll evaluate F of, I don't know, like 9 is my favorite number. So knock that out real quick. So as I'm walking around, all I'm really looking at is if the left side of your equation looks like that. Like, I'm pretty sure that we all got this part of it correct, except for me, who thought it was 47. But it looked great. Everybody, it looks like, had that notation down. So as long as you follow that same thing on your homework, you should be okay. So the second thing we're going to talk about today, and we will do a ton, like we will use this notation throughout the semester. So tomorrow in particular, we'll start doing some where we plug in expressions instead of just numbers. But to do a few more computationally, we're going to define what we call the net change. In F from A to B is the change in the function's value resulting from increasing, from changing X from A to B. So instead of X, I probably should have written input, but this is the change in your input. Oops. The resulting change in your output is what we call the net change. So anytime we'll see this language quite a bit throughout the semester, the idea of like the value of the function or the function's value. Anytime we talk about the value of a function, we're talking about its output. So when we talk about the change in the function's value, that represents the change in, so this is the change in the output. So if we had a graph of a function, and this is the input, and this is the output, let's call this A. That's an ugly graph. And this is B. So let's say this is the graph of our function. We have a point right here. I made this way too steep. Didn't even hit B. Oops. And we have a point right here. Well, the output of the function associated with an input of A is called f of A. And the output of the function associated with an input of B is called what? F of B, good. And so when we talk about net change, all we're talking about is the height difference in those 2 points. We're saying, like, how does y change when I move to the right on that graph from A to B? So this change right here is the net change. It is essentially the change in the y value that results from a specific change in the x value. So for example, if we go back to our previous example, we said f of x was 5x plus 3. If I want to find the net change in f from x equals 2 to maybe x equals 10. So one thing that you want to keep in mind about this is that when you're changing from 2 to 10, what is the change in the x value if you change from 2 to 10? In just the x value, forget the function for a minute. If I go from 2 to 10, the change is
8.
Positive or negative? Positive 8. Do I get that by doing 10 minus 2 or by doing 2 minus 10? 10 minus 2, right? We do where we ended up minus where we started. And so the same has to be true when you calculate the net change. So when I find the net change from A to B, I'm going to do f of B minus f of A, right? Where we ended up minus where we started. So if our x values are going from A to B, then the change in our y values is the y value associated with B minus the y value associated with A. You can think of like, I mean, sometimes we're going down, but if you think about like taking an elevator, right? If you go from the 2nd floor to the 10th floor, you're going up 8 floors, which you get by doing 10 minus 2, not 2 minus 10. And so even though it's written A to B, we're subtracting in the other order because we start with where we ended up and we subtract where we began. And so the net change from x equals 2 to x equals 10 is going to be f of 10. Just give myself more room. F of 10 minus f of 2. And there's ways to do, like, you can calculate one over here and one over here and then put them together, but even though it may seem more complex at this point, I think that if you get in the habit of writing this all as one expression, it's going to help you out later when we get to things like difference quotients, which you'll use to find, you'll use in calculus. So what I do is I just do like one big set of brackets to find f of 10, which is 5 times 10 plus 3. And then I do one big set of brackets for f of 2, so that's 5 times 2 plus 3. So this whole thing is my f of 10, and this whole thing is my f of 2. And then I'll just calculate what's in each set of brackets individually. So 5 times 10 is 50, plus 3 is 53, minus 13, which is 40. So the net change in f from x equals 2 to x equals 10 is positive 40, which means that the function increases by 40 when the x value increases from 2 to 10. Notice that I couldn't do anything with the number 10 and the number 2 individually, right? Like f of 10 minus f of 2 isn't the same as f of 10 minus 2, so like f of 8, because f of 10 represents that in this entire expression, and f of 2 represents this entire expression. So I have to do those calculations individually before I subtract. I can't like subtract the 10 and the 2 and plug it in and get a solution. So that's one thing you have to be a little bit careful of, because this looks so much like multiplication, like it feels like there should be some sort of distributing we can do or undistributing we can do, but it just doesn't work that way, because f of 10 is in and of itself a single symbol that represents that whole expression at 5 times 10 plus 3. And same for f of 2. So let's look at this in context. So let's say the function, P of D equals 14.7 plus 0.45 D gives the pressure in PSI, which is just a pressure unit, pounds per square inch. At a depth of D feet under the water. So like P of 10 would tell us the pressure 10 feet under the surface of the water. So what I want to find is P of 12 minus, let's say, P of 2. So we see that this is a net change, right? So P of 12 is the pressure 12 feet under the surface of the water. P of 2 is the pressure 2 feet under the surface of the water. And so subtracting those is going to give me like how the pressure how much the pressure changes when I dive from 2 feet to 12 feet. So we will calculate that the same way. So we're going to plug 12 in. And then plug 2 in. I said 12 and I wrote 2. I'm sorry. This is a 12. It doesn't help that they both have 2s in them, probably. There we go. And I'm going to ask you guys to help me with your calculators because none of us want to see me do that in my head. What is the first one? What's inside that first set of brackets? 20.1. 20.1. And that second one?
15.6.
Thank you. So that's like 4.5? Is that true? Okay. So what does that tell me? What is that 4.5?
Is that the PSI? Is that at 10 feet?
So,
How would you do it?
sorry, go ahead.
So depth of under the surface of the water?
So that's the tricky part of this is that 4.5 isn't actually a pressure. It's a change in pressure. So this is the pressure at 12 feet. This is the pressure at 2 feet. So when we subtract those, what we're finding is the difference in the pressure at 12 and 2 feet, which isn't necessarily the same as the pressure at 10 feet, right? The change in pressure as I dive from 2 feet to 12 feet isn't necessarily the same as what the pressure is going to be at 10 feet, which is in between the two. So what this tells me is that from a depth of 2 feet to a depth of 12 feet, and notice the order that we're using there, right? Because the thing we start with in the calculation is our ending point in practice, right? So, yes, go ahead.
Wouldn't it be depth from 12 feet to depth of 10 feet?
So, these numbers are our depths, right? And so, like I said, if you think about like going on an elevator, if we went from 2 to 12 on the elevator, that would change by a positive 10, right? So we're starting at our ending point and subtracting our beginning point to figure out the change from 2 to 12. So from a depth of 2 feet to a depth of 12 feet, the pressure increases 4.5 psi. So that 4.5 psi isn't actually a pressure at any depth. It's just telling us how much the pressure changed by when I dove from 2 to 12 feet. And we're going to do a bunch more of this tomorrow. So it is part of that lesson as well.